Welcome everyone. I see some familiar faces. This is Devicetree for beginners, and I'm sure I saw some faces on my previous talks about Devicetree, which means that I'm a terrible teacher of this topic, or you really like to listen to me. I hope I will be speaking here correctly. I mean, I was asked to have a fixed distance between my mouth and microphone, but I'm always gesticulating like a wild goose during the mating season, so I really hope I will stand still this time. So this is an introductory talk, right, about Devicetree, but I also have some few topics which might be useful for if you know the things. My name is Krzysztof Kozlowski. If you cannot pronounce my name, I go by Krzysztof. I work for Linaro. I'm a Devicetree bindings maintainer for the kernel. I also maintain several other subsystems in the kernel. I wrote a lot of patches around the DTS Devicetree. Recently, I mostly read them. So this is practical presentation. I also marked here some things with this bold and fancy color, and these are kind of common things which we see on the mailing list, so things to watch out, for example. When we talk about Devicetree, it's being used by multiple different operating systems and users, like U-boot, bootloader. So during the presentation, I focus on the kernel. I use the terms Linux kernel, but it can be understood in a broader context. However, when we speak about the, let's say, coding style, or how do we exactly enforce some rules, yeah, I work in the Linux kernel, so these are the Linux kernel coding styles. This is obviously incomplete talk. I have only 40 minutes. If you have more complex questions, go to the writing bindings. They are quite nice. It's like a kernel has a trouble of huge documentation which no one reads, and actually even more which is missing, right? If you ever try to learn how to send a patch, you start with the submitting patches. And I started it like whatever 12 years ago, and that time I read it. Now, submitting patches grew significantly, but the writing bindings document is very, very concise. Therefore, there is no excuse not to read it if you ever actually want to learn something there. Okay, so I will explain shortly what is Devicetree. I will say how the DTS looks like, if you never saw it. I will touch the more complex problem, what compatibility means. This is actually a common mistake. How the Devicetree binding looks like, what you could put to DTS and Devicetree binding. And at the end, I will mention that you can have an error-free life and be very, very happy. At least we'll be happy. So what's the Devicetree? It's a tree kind of devices. This is not a true logo. Actually, this is rather a data format to describe the hardware for the systems which cannot discover the firmware, the hardware. So such systems are Devicetree-based. In the case of ACPI systems like x86, you have the ACPI which will give you this information. Well, we don't have. And the term DTS means Devicetree sources, and these are this kind of textual representation of the Devicetree, and this is what we actually write. And this will be consumed by the DTC compiler, obviously. The output will be the DTB, which is the blob, the binary. The bindings, which also I mentioned during this talk, are kind of set of rules how to write DTS. And they also describe the actual contract between the Linux driver, Linux or other, let's say, bootloader, and the DTS. And that's also important because you cannot break this, or you shouldn't break this contract. Devicetree schema, or DT schema, is, let's say, a separate project, and the toolset which we currently use in Devicetree in the Linux kernel to validate the bindings, validate the DTS, and also this is the format of the bindings. The bindings are written in YAML syntax, but we try to avoid the YAML, so whenever we want to reference, rather use DT schema. Picture is worth 1,000 words, so just to illustrate it, we have DTS on one side. The compiler, DTC, takes it, produces blob. This is pretty straightforward. And then you have the bindings. The bindings create the rules on the DTS, how you should write the DTS. DT schema takes the bindings, takes something which is called meta schema. It resides in the DT schema repository. And together, it operates on the DTB and gives you this validation result. So I will also mention this at the end. And this validation means whether the DTS complies with the bindings. However, my talk focuses on the left part of the screen here. So how the DTS could look like. So I'm pretty sure that some of you know, but in the case you don't know, it's a textual representation, and usually it consists of multiple, let's say, nodes embedded within each other. So this is why it's a kind of a tree. So here I embedded connected entire description of a SoC and a board into one file. It keeps going. There's some SoC node. Let's go one kind of by one quickly through it. So it starts with the root node, and this is this opening bracket. In this root node, you will define what is this board about, so the model, FUKIT, and compatible. We'll have some list of CPUs, some sort of firmware provided services. I really remove here many boilerplate and many other unneeded things. But just to illustrate that we have some things like that. Usually also in DTS, we describe what sort of physical memory you have. And the funny thing is that the Linux kernel doesn't know itself. I mean, the DTS sources don't know. And the bootloader usually provides this information because bootloader might be actually more customized per the actual board you run on. By convention, entire SoC is part of its own SoC node. So this SoC is itself a bus, simple bus. I will briefly explain it, but it doesn't really matter. The point of view that in this SoC, you will have more and more nodes representing the sub-devices of the SoC. These devices usually are memory mapped I/O, and this is why they should be on this simple bus. And they will have their own children, and this is why you have the structure of the trees. So this is a sub-device of SoC, like some SPI controller or SPI controller. So how it could look like? So he has the compatible, he has some address space, because he needs to configure the hardware for the registers. And it also needs to describe how the children could look like, because SPI is a bus, which means that you might have more things that are going, right? And this is why you have this address and size cells properties. Both the address and size cells, they say how the children should be addressed. And the address is the thing after the ampersand, so this is this unit address. In the case of the SPI bus, the address is the chip select, so actually it's one number, one integer. But you could have more complex cases. You could have some memory-based buses, and then this address cells and size cells would be different. So this SPI bus have one device, which is a touch screen. This is a Goodix touch screen. It has an interrupt, it has the receipt GPIOs, and important property here is that these are active low or time level low, and these have actual meaning that they represent the hardware, and the Linux actually parses them. So if you make a mistake here, some source code can work, some source code might not work. Each device needs power, obviously, and there is also some kind of specific properties per this touchscreen, so defining its size in the pixels. There is no status property here, which means the device node is being enabled by default, and this is kind of common mistake that people say that I want it enabled. No, but rather everything is by default enabled. You just could disable something. Compatibility, that's quite common mistake here. So the most important property there, and actually the first property there, is the compatible. Compatible is a list of strings. The format is vendor, comma, device name. And each of such strings represents some sort of specific device. So we don't want here family names, we don't want here generic names of some sort of class of devices, wildcards. We want this to match the specific hardware, specific device. And there are three exceptions. There's like syscon and SimpleMFD. These are Linux-specific devices, compatibles. They obviously don't have the vendor, they don't have anything more, but these are exceptions. I said that it's a list. List could be from one element, then it's actually pretty simple, but it could have two elements. And the example here shows like some Qualcomm device where the device is 8750, and it's actually compatible with 6650, 6350, and this is why there are two entries. We call one front dedicated compatible and one fallback. The one on the farther side is the fallback. Fallback because you can just, if the front doesn't work, you fall there, fallback. And you always need a device-specific compatible. So this is also a common mistake that people use kind of reuse compatibles per different devices, which is not what we want. We still want something which is specific per your device. Even if you have fallback, even if devices are identical, you should have the front compatible. And this means that, so if you have such two compatibles, right, the Linux driver can bind, can start, can probe based on, both of them, right? Linux works in that way that it will always choose the front compatible, but it could also bind to the previous one. So the compatibility here means that Linux could choose one of them. If device can bind, if the device driver can bind through the fallback compatible, it means that it's compatible. If it will work, it means that it's compatible. Some features might not work, right? Because let's say this new device comes with something on top, so this might not work. But if you bind to the old one and you still operate correctly, then yeah, this is what the compatibility means. And the dedicated front compatible, especially in the case of the SoC, or some kind of, let's say, IO devices, this might not even be used at all. We all want the specific front one, even if it's not used by the Linux drivers, because the Linux drivers bind probe through the old one, through the fallback. And from that point of view, there is another aspect, like if you have compatible devices, right, and Linux cannot work via the fallback compatible, then the devices are not compatible, basically. So this would be a mistake to use this express compatibility in that way with the fallbacks if Linux cannot use it. So this leads us to the bindings and how to start, how the bindings look like, or how to start if you have to write it. Luckily, there's the example schema. So this is a file which usually we recommend to start writing one, or just find the recently reviewed binding. Please don't take something 5 years old. Even if I wrote it, my first bindings were quite different than I would write now, so don't take even my code as example. Start with the example schema, for example. If you create any bindings, remember that we have a rule that we want the file name to match the compatible. It's easier for us to find it. And we use the YAML syntax. There's some sort of boilerplate here, so just copy-paste. We want, of course, dual license, GPL and BSD. MIT also could work. And this file name is part of the ID, and this is used by DT schema itself. So from this, you already see that the device will be ROM BD79104, whatever. I just found it in a kernel. I like this binding. I will use that example. I have here colleagues who actually wrote it. And so this is why I said that you are not so bad in this job, since I take this as an example. So let's go through it. This is just a boilerplate, right? We want the binding to have a title because you want to know what hardware this is. And this is about the hardware, not about the Linux drivers. So don't mention the drivers if you can. There should be a maintainer. So person who cares about the hardware, not subsystem maintainer. So don't take the I2C maintainer, SPI maintainer. By the way, this is some kind of ADC, and which will be visible later. This is a SPI device, so on a SPI bus. We keep going. There can be a description of this hardware. If you describe something, say a few words. You can skip description if it's obvious. Just remember, describe the hardware, not the drivers. And then with the properties section in this YAML syntax, we list the properties which we expect for the DTS. And also, these are the properties which the Linux drivers will be able to use. We start with the compatible. This is the most important property. And here is a very simple case. Const means nothing else allowed. So this is only BD79104. For the purpose of this exercise, we could have something else. So instead of this const, imagine different case, right? We have a compatible. And we have two devices which are similar, but they are not compatible. Therefore, we enumerate them. So we allow one of these two. And this binding describes the case. You could have either 79104 or 79115. The more complex case is this compatibility, right? So when you have devices which are compatible between each other, then the typical syntax starts with one of, kind of one of two, one of many. And one option is just const. So you only allow 79104. Or other option is a list. In the bindings, we describe the list with the items keyword, and then after the items, we actually list the items. I mean, English is tricky here. So in that case, we say that the list will be consisting of 79115, it will be the front one, and 79104 as a fallback. So how did this could map to the DTS? So DTS would be like this. Either one or this. Either you have alone 79104, or you have a list of two. And this is very common syntax. And whenever a bindings maintainer asks you, your devices look compatible, please express the compatibility in the bindings. Probably this is how you should go. Or if you don't go like this, please say, yeah, my devices are not compatible because of, I don't know, like that, some reason. We keep going, compatible. Let's stay with the simple case of 71, compatible, not important now. This is a SPI device on the SPI bus. Therefore, for sure, it will have this unit address or this chip select. So this is expressed via reg property. And for obvious properties, you don't have to say anything else. The reg cannot be anything else. You just say max items once, cannot be more than one. This is IOO, so industrial input-output. So we want their cells. It's working on a SPI bus, so there is a maximum frequency it can work. All of these come from the kind of standard properties. And it requires power. No devices can work without power. And even if the Linux kernel can kind of provide you a dummy regulators, you should still describe the power there, usually based on the datasheet. I didn't mention here many other kind of vendor properties because it's a simple device and we have limited time. And all of these properties are kind of generic. Generic means that they come from the other common bindings, or they come from DT schema, or even from Devicetree specification. If you ever have a need for a custom property, then you would have a vendor prefix and description and type. It will get a bit more complex. Look at the example schema file. We finish with the properties. We have to say which properties are required. We mean required from the point of view of the hardware or the drivers, because this is contract between the Linux and the drivers. We require compatible by convention, chip select, you need chip select for almost always for a SPI device, and the power supplies are necessary because without power you couldn't work, even if Linux provide the dummy supplies. This is a SPI device, and less obvious syntax now is that you need to reference the other schema, which will bring everything created to the SPI. And we do it like this. We say this kind of ref, and then we say that schemas, SPIs, PR, peripheral properties. If you have I2C device, then usually we don't have it. If you have other devices, it depends. If you ever write a binding, please look at the, let's say, siblings, so the similar binding, similar devices in the Linux kernel sources. If you reference other schema, you use the unrelated properties first, and this means that only these properties are allowed, and only, the properties which you list, and the properties from this reference. If you don't have other reference, you use the additional properties first, which means that only what you list is allowed. And this makes the schema, the binding, complete and very specific in a way that you cannot, anything which is not listed will not be allowed. And this is what we want, because then the tools can point the mistakes. Binding should have an example, should one reasonable example. So here is some SPI imaginary bus, and there goes actually the DTS for this device. Because it's example, it should be enabled. Don't put the status property. You can add more examples. Usually there's no point to have more than one. Why this example there is also allows to validate the binding against this example DTS. And this is being used by the DT schema, and I will mention this later. Okay, more important question, and this is maybe you will help me here. So what we could put to the Devicetree bindings at DTS? Well, if you want to shorten everything, then only hardware or the firmware-related things, right? So you cannot put the Devicetree model, whatever you have drivers, choices. This is not a suitable place for Devicetree, because Devicetree describes the hardware or the firmware. So we don't want also the Linux driver choices. We don't want to even reference the drivers. We don't want operating system policies. We don't have the runtime knobs. Actually, runtime even is obvious because the Devicetree is static. So I have few questions. I will not wait for your answers, but please think it with your brain. Can you put this to DTS? I need some child node for MFD driver. I have a multifunctional driver, and I need to instantiate a child driver from the Linux point of view. So to instantiate a child driver, I would need to add a device node. Can I add such a device node to DTS based on this purpose? You can think about the answer. If you ever read my review, you will know that no. Now, why? Well, because you just said the reason you want to have such device node is the MFD Linux driver, and this is Linux specific thing. So sorry, this is not a valid reason, right? So, but there are exceptions. If this child of this multifunctional driver is some sort of reusable piece of component between different PMICs, right? Like RTC block there. Now, maybe this makes sense. It could be, right? Or for example, if your child has distinctive resources from the Devicetree point of view, so like a memory mapped I/O or some clocks, some resets, which the parent doesn't have, but the child, the resources of the child. Yeah, that's a good argument, right? And usually the answer from us would be default this to the parent, which means that whatever, I mean, this child should be part of the parent, and your drivers will instantiate it from the parent, and it's not a DTS property. Okay, imagine a situation, right? Imagine that your driver needs to notify other drivers about whatever hot plug events, whatever this term is in Linux kernel. Can you embed such information in DTS? That your driver needs to notify someone else there? Well, answer also would be no, right? Because I again said Linux that your driver has to do something. So instead of saying what your driver has to do, please describe the problem. And the hardware problem could be real here, right? So eventually this property could go to DTS, but how you describe it, sorry, I mean, I don't understand. I speak with hardware properties. I'm still saying about the drivers, right? So probably you get that in the next answer. So imagine that your driver needs to register power supply, some charger stuff for this device, but not for the other device. So maybe you have two devices, right? They're compatible, right? But one comes with the charger, other comes without charger, and your driver should, handle this, right? So can you put such information? Yeah, for this device, register the charger, the power supply. Well, so you know my answer, right? I'm repeating no. But in this case, because if you have two different devices, they have their own compatibles, and the compatible defines what sort of device you have, right? So in that case, one device has power supply, charger, yeah, it's defined by the compatible, other doesn't have. So your driver knows that, yeah, I'm working with this device, this compatible, I don't have the charger. So the compatible defines what the driver can or cannot do. This is not hot pluggable case, by the way, referring to the previous talk. Yeah, now let's say that you have a problem that you need to program some specific register value, like some register foo, and you want a property vendor, foo. Can you put it to DTS? Well, this is a programming registers is a hardware thing, right? Registers are hardware thing. I see that someone says no, someone says yes. So the answer depends. Because, yeah, it's programming registers in general is a very hardware thing, so it could go there. However, if you describe the problem, yeah, my driver has to do it, I will complain, please do describe the hardware problem, please describe the characteristic, maybe you can, because maybe it's not about the registers, because maybe, for example, it's an operating voltage, right? Or maybe it's a allowed current, so maybe there's a, please rephrase it. But eventually, programming registers could be allowed. I mean, it is allowed. Okay, I mentioned the voltages, another case. I want a vendor allowed voltages microvolt properties, so kind of list which voltages allowed for my new device. I have two devices, right? They're compatible. I mean, I have a new device that's compatible with the old one, but the new device, compatible with the old one, has a different voltages, and I want to restrict this number of voltages to the DTS. So if you listen to what I was saying earlier, probably you might get the answer that probably no. Because if devices, these are two different devices, are compatible, right? They have their own compatible front, and the compatible defines that. So this is already implied by the dedicated compatible. And therefore, for that case, this is actually not suitable property, even though the property is hardware related. Another property, hardware-related, clock frequency. And this is a common case in the Linux kernel. You can see it many places. You can see also this in the kernel patches, right? So imagine that person says that I need to program the clock frequency, and this is why I need clock frequency property. This is very hardware property, right? Can you put it to DTS? Well, yes and no, right? Depends. So this is complex. So first of all, if you need to program some other clock, then this clock is input to you, then you should have clocks property. If you have clocks property, you can get the frequency with the common clock framework, with the Linux framework, clock get rate. You can also set the frequency, clock set rate, right? However, maybe on the other hand, you need to set the frequency of some other clock, and for this we have already a property called assign clock rates. Therefore, usually answer for the clock frequency that is a legacy property, and there are other ways to do it. Therefore, you shouldn't use this one. Very generic question. Next one, I just add a vendor foo property, whatever, for my hardware need? Well, this is very generic, therefore I will not torture you. Please always check if there is a other property doing the same, in a way that maybe there's a generic property like a common to add to every binding, and then please use the generic properties, not define every time the same for your driver. Okay, I'm getting to the difficult topics now. So, very imaginary case, right? You have a SoC. The SoC has PCI Express PHYs. It has 2 PHYs, and these PHYs are almost identical. They're compatible with each other, right? But there is a minor difference, so they're not exactly identical. And I need to define whether this is like an instance 1 and instance 2. I need to differentiate them, because there's this minor difference between them, but they are compatible, right? So the drivers will know that I have this instance 1, or for instance 1 I have to do like this. For instance 2 I have to do something else. So can I have such property? Well, probably, or who knows, right? Usually we don't want it. So we don't want the instance IDs. Why? Because maybe there's another property saying it. For example, in case of the PCI Express PHY, there could be number of lanes. And maybe this is the difference between these 2 devices, that they have different lanes, so you have it. Or maybe they're not actually compatible, right? Maybe there's a difference in programming model, and programming model is what defines the compatible, so maybe you need different compatible for the device. And for specific cases, the consumer and provider relationship can define it. So if it is a PHY, then it's a PHY provider, and there will be PHY consumer. And this PHY consumer maybe will tell you, like, imagine that the PHY provider could support different types of PHY. Like I can work as a PCI Express PHY, but I can also be, I don't know, some serial SerDes or whatever, right? So the consumer can also reference the provider giving the argument, and this argument, maybe it's enough for you to solve your case, this instance ID. We're getting to the end of the talk. So I mentioned that we have the bindings and that it can help you. They can save your time. Why? Because this YAML schema, actually YAML syntax and the DT schema, this allows to validate both the bindings and DTS. So here are kind of practical comments which you are expected actually to use whenever you create new bindings. So first of all, you can check whether the binding is correct, and this is the makefile target DT binding check. You can narrow it per the specific schema, or you can run it for entire Linux kernel sources. You can also validate whether the DTS, so the sources, are conformant to the bindings. For this, you have the DTBS check. So here you have to remember that you need the cross-compile options or your ARC if you do it for some different architecture, right? Make DTBS check might take a lot of time. You can narrow which binding you want to use, and for this you can use the same argument, DT schema files. It's still, if you want to shorten further, you can test one DTS, and if you want to test one DTS, then you actually use the DTB target. So this would be the Qualcomm, here in this example, Qualcomm SM84, whatever, DTB. And you can also do this with a specific schema. So one board against the schema, against one binding. So this is, let's say, the combination. Yeah, and this leads us to the end, right? Yeah, we're very fast. So that's it from the talk. Any questions? Yeah, there is a mic next.
Thanks for the refreshment. So about Devicetree binding examples, I believe they are seen as examples for Devicetree writers, mostly. But as a Devicetree binding writer myself, I often use them to check whether all the conditions have been properly verified. And for checking that, I'm actually adding good examples and also explicitly bad examples on my side to verify that I'm catching the errors. But I'm always removing this part because that's not what the examples are for in the first place, I guess. So did you ever consider keeping those, well, maybe adding extra examples that we could use to verify that the bindings will remain correct, especially since they are mostly, well, often very more complex than just the current file we are looking at because of the references. And well.
So if you ask whether we want to keep incorrect examples in the bindings,
yes,
then probably the answer would be no, because we don't keep incorrect code. And the same if you, I don't know, if you write C code, right? You also don't add weird code just to check if your compiler finds this as a warning, right? But I could see your example that maybe the example should kind of, for complex devices, should cover possible combinations, right? But usually the answer would be, yeah, then remove it, right? And then the binding, by the way, is also not touched, and you know, we don't keep bad code in the kernel. Yeah, but I understand the point. There's a behind you question.
Yeah, so there are still bindings that use the TXT format in the kernel, right? Is there anything in particular to look out for someone who wants to like maybe rewrite a binding in the new YAML format?
So if you ask what, this is nice task for starting your, let's say, contributions. So it's always welcomed. You can always do it. So the guideline here would be that please take the bindings which have users. The user means like a most likely DTS. So there's an in-kernel DTS and this text binding, right? Do it. And nowadays, because Rob Herring, the other Devicetree binding maintainer, he was actually using a trained algorithm to massively convert it. You can check his kernel org repo. You can find there kind of a lot of, let's say, this massively converted things which he did in upstream, and just take it, customize it, and build on top. He will not mind, because we just want everything to be converted. So if you find such bindings, convert it, and also check if there are no duplicates on the mailing list, like someone is doing this on.
Okay, thank you.
No questions. I don't see hands. Yeah, good. Thanks. I will have more. I will have speaking hours tomorrow. There is more question in the back. You're saved. So you can also come tomorrow for the speaker office hours, and I don't know, whatever questions you are afraid to ask in public.
Yeah. Thanks for the talk. I have a question, and I'm sure you will hate it, but I will still ask it. I have often the problem that I have, for the very same device, multiple drivers. So I have two drivers that work for the same device. And as you have greatly expressed, the Devicetree describes only hardware. But I really, really, really would like to have a way that I can define this preference somehow in a Devicetree, which driver the kernel should bind first. So I know this is...
You will not get different answer. Yeah, I remember your parset, yeah.
What I think about is, could we maybe add something to the status property, that the status property says bind manually, that the node is not disabled, but then I can just using the sysfs bind on my own, because otherwise I have to first unbind the wrong driver first, and this is something I would like to avoid. So I'm perfectly fine with binding using sysfs, but what I hate is first unbinding the wrong driver.
So the status property has, I think, 4 values: reserved, failed, OK, and disabled, right? And you would have to fifth value, but this fifth would be still kind of system specific, right? Like that you partition for the XNMI, right? That's your use case. I remember the patch, of course. Could work. I mean, that's the cleanest solution I know.
Yeah, so
propose. Let's see what Rob will tell.
Okay, then I will send the patch.
Yeah, make your case, right? Make your case.
Okay, thank you.
Another hands up? No? Okay, great. Thanks very much. I'll see you tomorrow.